lecture is about drum level methods of compensation, part 2. In this lecture, we shall be talking about compensation equation derivations. For this, calibration of the level transmitter shall be at atmospheric pressure and compensation shall be at other pressures. It is hoped that this lecture is going to be useful to you. Please press like button. Please subscribe. Calibration at atmospheric pressure with compensation at other pressures. The differential pressure transmitter is calibrated in the same way it would be if drum pressure was not a problem. Compensation curves can be generated without knowing the exact normal operating pressure. Once these curves are generated, they can be used even if the normal operating pressure changes. This is the table which is showing specific weights versus drum pressure. So here we are showing the specific weights for water, that is at the saturation temperature, steam, that is at the saturation temperature, and a specific weight for the water which is in the reference leg. It will be at 100 degree Fahrenheit, but the pressure will be same as the saturation pressure in the drum. Differential pressure calculation. A detailed schematic representation of the basic reservoir column installation can be seen in the figure shown in the next slide. In this installation, the portion of the reference leg between the level measurement taps is assumed to be at 100 degrees Fahrenheit, which is a reasonable assumption for a boiler whose drum is located indoors. Here is the drum level reservoir column basic installation. Here we can see that H is the difference between lower tapping point and the upper tapping point. There is subcooled water at drum saturation pressure in the reference leg. Both the legs which are connected with the level transmitter are having the same temperature and pressure in both legs. HS is the height of steam column and HW is the height of the water column above the lower tapping point. In this diagram, we are defining NWL, that is normal water level. Normal water level is the level at which we are supposed to keep the drum water. So here we have defined below the normal level is minus x, and above the normal level is plus y, h equal to x plus y. Normal water level is represented by 0 inch, which yields a drum level indication range of the form minus x inch to plus y inch for 4 to 20 milliampere DC. The pressure at the reference leg connection to the DP meter is formed from two components. One component is the static drum pressure, which we also call as saturation drum pressure, and the other is the pressure resulting from the weight of the water in the reference leg. The weight of the water in the reference leg is the product of the overall height of the water column multiplied by its density. The reference leg temperature is assumed to be 100 degree Fahrenheit, having height of h. The sensing leg pressure is the sum of the height of the water column leg h subscript w multiplied by its density plus the height of the steam column leg h subscript s multiplied by its density plus drum static pressure. It should be noted that if the reference leg temperature varies widely from the 100 degree Fahrenheit assumption, the resulting measurement error may be significant. Consideration could also be given to measuring this temperature and including it in the compensation equation. The differential pressure measured by a transmitter for a particular level will then be the pressure difference between reference leg and the sensing leg. When generating compensation equations, the differential pressure transmitter is assumed to be calibrated in units of inches of water at 68 degree Fahrenheit. This is a normal assumption. From figure 2 and the preceding paragraphs, we can see that the expected measured differential pressure for a given level and drum pressure can be calculated as described in equation 1 written in next slide. Here is the equation number 1, and below this equation we have given the definition of various terms used in this equation. Please go through these definitions carefully. Equation 1. The h variables in the above equation are referenced from the height of the sensing leg connection to the drum. This is a rather complex formula. However, more simple formulas can be derived for the conditions that exist at the extremes of our measurement range. Definition of dP subscript L. In this diagram, the drum water is at the lower tapping point. Equation 2. At the condition where the water level is at the lowest point to be measured, equation 1 simplifies as shown. In this diagram, the drum water is at the level at which we are having the higher tapping point. Definition of dP subscript U. Equation 3. At the condition where the water level is at the uppermost point to be measured, equation 1 simplifies to equation 3, namely dP subscript U equal to the expression shown. Equation 4. Note from the figure 2 that at the 0 psig and 68 degree Fahrenheit, our differential pressure transmitter would be calibrated for H-inch H2O to 0-inch H2O for 4 to 20 milliampere DC. That is equation 4. Note from equation 4 that our drum level transmitter must be reverse acting. For a decrease in differential pressure, the output signal must increase. If a digital control system is being used, the transmitter output can be inverted in the software of the DCS. Equation 5. H-inch H2O to 0-inch H2O for 4 to 20 milliampere DC. That is equation 4. H equal to X plus Y minus X inches to plus Y inches for 4 to 20 milliampere DC, equation 5. An equation can be derived for this control system scaled input In as follows: In equal to H minus dP minus X, equation 6. Since H equal to X plus Y, we can rewrite equation 6 as follows: In equal to Y minus dP, equation 7. So at NWL and 68 degree Fahrenheit water in the drum, the transmitter input to the control system would read Y inches differential and the scaled control system input would read 0 inches. From figure 2, we can see that our measurement span S at any saturation pressure will be S equal to dP subscript L minus dP subscript U, equation 8. To properly correct or compensate a drum level transmitter for any saturation pressure above 0 psig, the actual pressure must be measured and used to gain and bias our drum level signal by an amount related to the actual change in the water and steam density. Equation 9. Substituting equation 2 and 3 into equation 8 gives us equation 9 as shown alongside. Equation 10. Equation 9 will simplify as follows, as shown in the alongside. Finally, we get S equal to H multiplied by capital G. Equation 11. Finally, we get equation 11 as S equal to H multiplied by capital G, where G is defined side by. Measurement span S relates the sensitivity of our compensation output to a change in the input. The change in output for a given change in input can be written as D out equal to D in upon capital G, where G is equal to the gain derived in equation 11. DIN is the change in scale control system input, see equation 6. D out equal to change in scale compensation output. To change equation 12 to a form that relates actual inputs to outputs, we must subtract whatever constant is required to bring the output to 0 when the transmitter input relates to normal water level NWL. Equation 13. The subtraction constant K can therefore be calculated by the formula capital K equal to NWL input upon capital G. The basic compensation equation for reference column installations can be written as out equal to in multiplied 1 upon G minus NWL input upon G. Conclusion. Now use equation 14 to program the control system. Another way to write the compensation equation is out equal to in multiplied by Q plus P, equation 15, where out equal to the compensated output in inches. In is equal to the scaled control system input in inches. Then Q, the gain factor, equation 16 is defined as shown. B equal to the bias factor minus NWL input multiplied by Q, equation 17. Now we can see that equation 15 is nothing but equation of a straight line. So in which we have to determine Q and we have to determine capital B. Combining equation 6 and 17 for the NWL condition results in capital B equal to the bias factor equal to dP NWL minus X multiplied by Q. Equation 18. For a particular pressure, the NWL differential pressure dP NWL can be calculated using equation 1. The term X is the same one that was used in equations 5 and 6. Now use equations 15 through 18 to program the control system. It is hoped that this lecture is useful to you. Please press like. Please subscribe. Practical considerations. While installing the drum level transmitter, some practical considerations are very important. These and other important aspects shall be discussed in a subsequent lecture.